So what's the implication? Well, the implication is, well, let me talk first about mathematical implication. There is a geometric point of view on functions. And that point of view is very different from the view of, from considering graph of a function. So I'm still talking about functions of one variable, the usual functions from Calc 1. But my geometric point of view is going to deal with questions like, what is the angle between two functions? Have you ever thought about two functions having angle between them? And why would anybody care about having angle between functions if nobody can imagine that? So let me tell you first how to introduce this concept of angle between functions. Right? And then I will tell you why people would care about it. So the idea is to introduce a product and call it a dot product of functions. Haven't defined it yet. And here's the definition. If I want to dot product two functions, I will integrate the usual product f of x times g of x with respect to that variable x from negative pi to pi. And this is my definition of the dot product. And of course, I cannot say that whatever I want to define being a dot product can be written as any random formula. Right? There are some crucial properties that dot product has to satisfy. It must be a product on the first place. Right? What does it mean to be a product? Well, that means that if I dot product f with a sum of two different functions, g plus h, it must be the same as f dot product g plus f dot product h. Distributivity must hold. Now, does it? What if I integrate the product of f times g plus h? Well, I know distributivity holds for the usual multiplication. So I can distribute there f times g plus f times h. And then I can divide it into two integrals. F times g plus f times h. And I recognize those integrals as exactly dot products. The first is f dot product g, the second is f dot product h. All right, so that's the first crucial thing I need about the dot product. And the next thing I will need is the fact that if I dot product a function with itself, it's not going to be 0. It's always going to be greater or equal than 0. It's always positive. It will be 0 only if the function is constantly 0. And why is that? Well, because if you look at the integral from negative pi to pi of f times f, well, that thing is a square. And you are integrating a positive function. And whenever you integrate a positive function, the result is going to be positive unless the function is constantly 0 and there is no area below the graph. Right? Now, what's the advantage of that? Well, the key advantage of this positivity is that now I can say, I can define the magnitude of the function. to be the square root of the dot product of the function with itself. In exactly the same way as we know that for any vector, the magnitude of a vector is a square root of the dot product of the vector with itself. So I'm just mimicking the vector definitions. So I know what the magnitude is, and I know what the dot product is. Now I can define what the angle is. Cosine of the angle between two functions. You should all know that formula by now, right? It is f dot product g divided by magnitude of f times magnitude of g. The only thing is that the meaning of those magnitudes and the dot product is the integral. But now I have a meaningful way of saying what the angle is between any two functions. Okay, so that's the computational part. Now, why does anybody care about it? Well, why do we care about angles in geometry? What's important about angles? What's important about knowing that there is some angle between these two vectors? Let's say v and u. Take two vectors in a plane and you know, well, there is an angle between them. Well, the importance for my implications in physics is going to be the recognizing whether this angle is right or not. I will not care too much about the exact value, whether it's 58 degrees or 57. I will definitely care whether it's right or not. And why do I? Here's the thing. I can look at the sum of the two vectors. U plus v. And then my question would be about how this sum behaves when I change one of the vectors only. But the way I measure this behavior is by projecting the sum onto the direction of v. So I'm looking now at projection of the sum onto v. Now what I can claim is that if I change v, and if I change u, instead of u I choose 2u, then of course my sum will change. It will be 2u plus v. And in this picture you see that projection of 2u plus v on v is different. So this projection depends on u. And the key thing here is that this projection is independent of u if the two vectors are perpendicular. So this projection of the sum onto one of the vectors is independent of u if u is perpendicular to v. Which means exactly that u dot v equals 0. And that's exactly where the dot product comes in. And that's exactly how I can bring this idea to functions. So what this says is that perpendicularity is about independence in some sense. So that means if I define the concept of angle or the dot product, and I see that f dot product g is 0, that means those two functions are independent in some sense.